Yeah.
Not just me to think that, but one of his friends is gonna think that.
Well, I don't have any like friends on that thing. Cause it's not like,
There are some people I recognize.
like iPhone.
Yes.
Like, you're doing well.
Yeah. So his name is Johnson.
Like, you can follow people.
Now to explain her, it's all.
No, I mean, that was, we want. Get mad at that.
Okay, so let's finish up the last problem and then we'll wrap up. So the last problem, you're given with mass matrix and stiffness matrix. So the equation of motion. Okay, so the first question is natural frequencies, and the next one is mode shapes. So we have done this for many times, so let's see. So okay, eigen problem is k minus omega squared m p is equal to 0. So 1, 0, 0, 2 minus 2 omega squared. Oh, nope. Sorry. 2 minus 1 minus 1, 3 minus omega squared 0, 0, 2 omega squared. You know that this should be a singular matrix, meaning the determinant has to be 0. Uh, 2 minus omega squared minus 1 minus 1 3 minus 2 omega squared is 0. So 2 minus omega squared 3 minus 2 omega squared minus 1 is equal to 0. This is the characteristic equation. So omega 4 minus 4 minus 3 minus 7 plus 6 minus 1, 5. If I do it correctly. Somehow I cannot think this morning. 1 minus 1, 3, 2, 3 minus 2.
I think it's -6 W squared. Yeah, minus 2 omega 4. 2 omega 4 minus 6 W squared plus 5.
Omega 4. Yeah. Now it's correct? I don't know. Okay, so minus 4.
6 omega squared.
6 omega squared?
Sorry.
Okay, yeah. Okay, so this is the equation. So let's say lambda is omega squared, then 2 lambda squared minus 7 lambda plus 5 is 0. Lambda is 4. Minus b plus minus 49 minus 4ac, which is 4, 7 plus minus 9 is 3. So lambda 1 is 410, which is 25. Lambda 2 is 4, 4, which is 1. So you know that natural, let's say this is 1, this is 2. Let's order from the smallest. So omega 1 is going to be square root of that, which is 1 radians per second. And then omega 2 is square root of 5/2 radians per second. Let's check. K 2 minus 1 minus 1 3 M 1 0 0 2 B D E I G A M. Okay, so lambda 1 is 1. So omega 1 is square root of 1. Lambda 2 is 2.5. Okay, yeah. Okay, so this seems to be correct. And if you, so that's number 1. Number 2, mode shapes. So for mode shape, you have 2 mode shapes. One associated 1 radians per second, and the other one associated with square root of 5/2 radians per second. So what you do is you substitute 1 into this equation. Yeah, so this equation. So if so this is 2 minus omega squared minus 1 minus 1 3 minus omega squared P1 P2 has to be 0 0. So if you put 1, it's going to be 2 minus 1 is 1 minus 1 minus 1 3 minus 1 is 2. Oh, 3 minus 2. Okay, so 1 1. P1 P2 is 0 0. So if in order to compute the mode shapes, you substitute 1 here, right? First, then what happens is 1 minus P2 is 0. So P2 has to be 1, right? So if I choose P1 and P2 to be 1, 1, 1 minus 1 is 0, minus 1, 1 is 0. So you can see that P1, mode shape 1 is 1, 1. So what it tells me is the mode, the first one, x1 and x2, it's moving in unison with natural frequency of 1 radians per second, which is shown in here. It's shown as minus 0.57735 and minus 0.57735. So it's moving together. I already mentioned that the MATLAB gives you the normalized vector, meaning it normalizes with the length of the vector. So it's going to be like one squared, 1 squared. So this is going to be 0.57735. And negative, I don't know how MATLAB computes this. It just normalizes it. It doesn't care about the direction. So your mode shape is not unique. It's the relation between the first element and second element is unique, meaning it's same, right? The ratio is same. This divided by this is same. You can do the same thing here for the second mass. The 2 minus 2 over 5 minus 1 minus 1 3 minus 2 times omega squared is 5. P1 P2 is 0. And this is 2 over 4 minus 2 1 minus 1 minus 1. Wait, did I do it correctly? Minus 2. P1 P2 is 0 0. So if I choose this one as 1, minus half minus P2 is 0. P2 is minus half. So you can see that P2 is going to be 1 minus 1 half. And you can check with the second one. Minus 1, minus 2 times minus 1 half is 1. Minus 1 plus 1, 0. So you can see that this is the mode shape of the second flexible mode. And if you want to have a mode shape that is normalized, you can also do that. 1 squared plus minus 1/2 squared. You can always normalize the vector. But the relationship is when the first x moves by 1, the other one moves by half on the other direction, right? So, and the MATLAB says this move by 0.81. The second one moved by 0.40. So it's half and opposite direction. Half and opposite direction. Okay, so that's what we have looked at before. So, but the third question is show that mode 1 is orthogonal to mode 2 with respect to the stiffness matrix K. So before we do that, let's see if we can come up with a modal transformation. So modal transformation says now we have, let's use this mode shapes. So now we have a mode shape 1, 1, that's the first mode shape. 1 minus f. So these are the two mode shapes. And remember the modal transformation is defined as x1, x2 is defined as modal matrix times Q1 and Q2, right? You remember this, the modal transformation? So essentially you have first mode shape and second mode shape, and you have Q1 and Q2. The Q1 multiplies, so remember, these are the first mode shape. The first mode shape only multiplies to Q1. See, Q1, Q2, Q1, Q2, right? So you can see that the first mode shape is only multiplied to Q1. So the Q1 represents the simple harmonic motion at frequency omega 1. This is the temporal response to omega 1, right? And this is the temporal response with omega 2. Right? And these are the shapes. So when you go from only the temporal part to the actual physical coordinates, you have to distribute first mode and second mode response into the correct shape. So you distribute Q11 and then, so this, according to this mode shape. So we call this modal matrix P, right? X is equal to PQ. So this is the key thing. So this is the definition where you can transform your coordinates from modal coordinates to physical coordinate to modal coordinate. Right? So our original equation was written as mx double dot plus k x is equal to 0. And then we substitute this back into x. Right? So like this. And then we also know that phi is just a constant matrix, fixed mode shape. So you know that X dot is P Q dot, and X double dot is P Q double dot. So you substitute this one here and this one here, then you can rewrite this equation as M X double dot, M P Q plus double dot plus K P Q is equal to 0. And then remember that we pre-multiply P inverse. And then we define this as a modal mass, MQ double dot plus KQ is equal to 0. Where M prime, which is the modal mass, is P inverse M phi, and modal stiffness is phi inverse K phi. So let's do this in MATLAB and see what our modal matrix and modal stiffness is. So let's not worry about the one that MATLAB gave me. Let's define our phi matrix with the mode shapes that we determined. So the mode shapes we determined is 1, 1, and 1 minus half, right? So let's use the one that we came up with. Let's use these as our mode shapes to construct the modal matrix. So our modal matrix is 1, 1, 1 minus half. Okay, so that's so this is our P matrix. 1, 1, that's the first mode shape. The second mode shape was 1 minus half. Right? And we compute modal mass, which is P inverse M P. So by the way, this transformation is called similarity transformation, meaning you're trying to transfer into coordinates from X to P, Q, but with same dimension as the mass. So this will give you the same dimension, and by pre-multiplying phi inverse. So that you can compare the you can come up with a new mass, and then with a similar format, similarity transformation. Similarity transformation. I think that's what it is called. So phi inverse m phi, right? So let's compute inverse of phi times m times phi. So this becomes our modal mass. Wait, is our m correct?
Well, that should be kept prime, right? Yeah.
Oh, say that again.
That the inverse B and B should be M prime, not M. Not the,
Our phi inverse.
Oh, yeah.
Phi is our M.
Oh, sorry. Let's do it again. M is, let's say, M is this, K is this, and our P is this. P 1 minus 1.
Oh, is it like two, not like one?
Negative 2, is it?
For the B. It's gonna be 1, -2
Which one is negative 2?
instead of the -1/2.
This one?
Yeah.
Was it negative 2? Let's see. No, half, right? So first one is 1, this is half, and the opposite direction. So the P is correct. P transpose times okay. So not giving me. Okay. So what the orthogonality means is when you so instead of using yeah, okay, so only this one works. Wait,
Probably
the
something weird with how calculates inverse or something.
yeah, so what happens is, let's say that's the mode shape MATLAB created. Inverse of V times M times V. So V times K times yeah. So orthogonality, what orthogonality means that the inverse is its transpose. So typical similarity transformation, you multiply inverse here, right? But the modal transformation, instead of inverse, you can use transpose. P transpose M phi Q double dot plus P transpose K phi Q is equal to 0. So this becomes the new modal mass and modal stiffness. So forget about this. Modal transformation, you use the transpose instead of an inverse. So this is what you pre-multiply, phi transpose. So if you multiply phi transpose, what happens is your modal mass now is, let's say, my modal matrix is this, mass matrix, stiffness matrix. So M prime is phi transpose times M times P. So that's the new modal mass, 3001.5. And then our modal stiffness, K prime, is P transpose times K times P. So that becomes our modal stiffness. So let's write this. So after using this modal matrix and transform X to Q using this definition of new modal matrix and modal stiffness, and you get new modal matrix, which is going to be 3001.5 Q1 double dot Q2 double dot plus 3003.75 Q1 Q2 is equal to 0. So this is the equation of motion written in modal coordinate. Original equation of motion was 1002 x1 x2 double dot plus 2 minus 1 minus 1 3 x1 x2 is going to be 0. So compare this equation in physical coordinate, and this is in modal coordinate, right? So this coordinate, you have K matrix, which is coupled. So you have x1 and x2, right? In the first equation. The second equation also has minus x1, 3x2. So it's coupled equations. However, if you write your equation in modal coordinates, the first equation 3q1 double dot plus 3q1 is 0, right? So the first equation is 3q1 double dot plus 3q1 is equal to 0, or q1 double dot plus q1 is equal to 0. So this is the first equation. Only a equation in terms of Q1. If you look at the second equation, 1.5 Q2 double dot plus 3.75 Q2 is equal to 0. Or Q2 double dot plus plus 3.75 over 1.5 Q2 is equal to 0. So you have, this is the second equation, right? Remember, our natural frequency was omega 1 was 1, omega 2 was 2.5, square root of 5 over 2, right? So we know that you can write this as Q1 double dot plus omega 1 square Q1 is equal to 0, right? Q1 is 1. Q1 is omega is 1, and omega 2 was square root of 5 over 2, right? So this must be 5 over 2, right? 2.5. 5 divided by 1.5. Yeah, 2.5. So this is 2.5. So this is 2.5, 5 over 2, right? So you can see that now your equation of motion in motor coordinates is written in first order differential equation. So which has effective mass and spring such that it comes out with a natural frequency omega 1, right? K1, M1. So the M1 is the motor mass 3. K1 is the motor stiffness 3. So that the natural frequency is square root of K over M, right? The motor mass. So this is motor mass 3, motor stiffness 3, so that you have natural frequency 1. Same thing. This one has motor mass of 1.5 and then motor stiffness of 3.75, so that it will have a natural frequency which is square root of 5 over 2. Right? So if you write the equation of motion in motor coordinates, you are essentially decouple the coupled equations in physical coordinate into set of uncoupled single order differential equations. And the orthogonality of the mode shapes is basically checked by looking at this matrix where phi transpose k phi resulting in a diagonal matrix, because it was coupled originally, k was coupled, but by using the transpose and then phi transpose k phi, you have a modal stiffness which is uncoupled, right? You have a 0 terms at the off diagonal. You only have a diagonal terms. So that's the characteristics of mode shapes being orthogonal modes, so that this transformation is resulting in an uncoupled. So you just show that by by doing the modal transformation, the modal stiffness matrix is diagonal respect to the original using the original stiffness matrix and show that it's a diagonal matrix, then you can, that shows that your mode shapes are orthogonal. So now the last question is how to, so initial conditions are given. Determine the initial conditions in modal coordinates. So let's say initial conditions are given as x1, x1 0 is 1, and x1 dot 0 is 0, x2 dot x2 0 is 0, x2 dot 0 is 0. So these are the initial conditions, right, given. And then I would like to determine the solution of this, right? Remember, if you want to solve this in terms of x of t, x1 of t, x2 of t, it's difficult to do it here, right? Because you don't know how to solve for x1 and x2 unless you do something some algebra, which is not as straightforward as this. But how about this one? This one, can you solve for q1? Right? Because q1 is a cosine omega 1t plus b sine omega q1 is a sine a1 b1 cosine omega sine omega 1t, and this one q2 is a2 cosine omega 2t. Omega 2 is square root of 5 over 2. Omega 1 is square root of 1 plus b2 sine omega 2t, right? So in order to solve for this and this, you need to determine a1, b1, a2, b2, right? So a1, b1, a2, b2 is computed from initial conditions written in Q, right? So Q1 at 0, Q1 dot at 0. So if we have these two, we can compute a1 and b1, right? How about a2 and b2? If you have Q2 0 at time 0 and Q2 dot at 0, then we can compute a2, b2, right? So if we have initial conditions written in modal coordinates, then we can solve for q1 and q2. And once you have q1 and q2, you multiply this matrix to go to x1 and x2, right? So it's much easier to solve your differential equation if you write the equation of motion in modal coordinates using modal transformation, and then solve for q1 and q2, and then go back to physical coordinates. Because in modal coordinates, all the equations are uncoupled, and each equation is a second order differential equation, which we know how to solve it because each equation is a simple harmonic motion, right? The solution is a simple harmonic motion because it's a single degree of freedom spring mass system equivalently, so that you can, that the solution form. And if you know the initial conditions, then you can go back. Only thing is, how can we determine these initial conditions? Q10, Q1.0, Q20, and Q2.0. That comes from the original initial conditions. X1 in physical coordinates, the initial condition is given. Now, I need to find x q1 q1 dot q2 q2 dot. I need to determine the initial conditions written in modal coordinates from physical coordinates. And the way to determine the initial conditions in modal coordinates from physical coordinates is again using this modal transformation, right? So you know that x1, x2 is 1, 1, 1, 1 half, q1 and q2. And same thing, dots, velocities, it's 1, 1, 1 minus half, q1 dot, q2 dot, right? So you can see that q1, q2 is this phi inverse x, x1, x2, right? Same thing, q1 dot, q2 dot is phi inverse x1 dot, x2 dot, right? So you know that x1 is 1, x1 dot is 0. So you just take this vector and then pre-multiply phi inverse. That will give you q1 and q2, right? So what you can do is multiply inverse of phi, and then initial condition in physical coordinate, it was 1 and 0 for the positions. So it gives me that my initial condition Q0 and Q10 and Q20 is 0.333 and then 0.6667. And then same thing, 0, 0. So if it's 0, 0, velocity is also 0. So it's going to be 0, 0, right? So you can compute the initial conditions in physical coordinate into modal coordinate, which is 0.6667 and 0. So you can see that initial condition 1, 0, 0, 0 corresponds to initial condition Q1 is 0.333, Q1 dot is 0, Q2 is 0.667, and Q2 is 0. And using that, you solve for A1 and B1, A2 and B2. So that gives you the complete solution of the response in modal coordinates. And then using the complete solution in modal coordinates, transform back to X. That's how you compute the response in physical coordinates. Does that make sense? In the final exam, I didn't include these questions because I think it's a little bit out of scope, and response, you can easily compute it from using MATLAB nowadays. But the most important thing is you need to know what the model transformation is, right? How to compute the mode shapes, and see if you can transform the equation of motion written in physical coordinate into modal coordinate. So there will be a question on how to transform your equation of motion written in physical coordinate into modal coordinates. Right? And for that, you need the mode shapes, right? And then using the mode shapes, modal matrix, you ended up with a modal matrix and modal stiffness. And if you divide the stiffness divided by m for each row, you get a equation of motion. So what I'm saying is this equation you can rewrite as set of uncoupled equation, which is q1 double dot q2 double dot plus now q1 q2 is 0 0. So what I'm doing is I'm now divide this by m. And normally you cannot divide the matrix, right? Because the modal equation of motion written in modal coordinates is diagonal matrix, diagonal. M is diagonal, K is diagonal. So this diagonal element will be the omega 1, omega 2, right? 0, 0 square. Right? So the diagonal element will be the natural frequency square. So you can see that physical coordinates transform into modal coordinates. It's going to be in the form of q double dot plus 2 zeta omega n q dot. If you have a damping, right? But omega n square q is equal to 0. So that's the standard form for single degree of freedom system, but with many different modes, right? So if you write it in this way, you can add, it's easy to add damping, right? Because now you are in modal, so you can add damping as a diagonal component. So we call this matrix spectral matrix, whose diagonal components are eigenvalues or the natural frequency squares. So we call this spectral matrix. So if you look at the MATLAB, when I do EIG of K and M, and then remember I did B and D. D gives you the P, modal transformation matrix, modal matrix. And D is the spectral matrix. Basically, these are these matrix. So you already know by looking at these two matrices, you can write the equation of motion in modal coordinates. Modal coordinates, you can write it as natural frequency and damping ratio, right? Because it's all diagonal, so you can divide the K with M to get the natural frequencies. So that is the last material. And if you're going into this this area, I think you will continue this. So I have the graded midterm, so you can pick up. And those who did it online, I'll email you those. And the Friday we'll have a test, 2 hours, 3 hours here. I heard that this room may be only available for 2 hours, but we can move after 2 hours if you're still working on it, to some other office, some other room. But I hope that you can finish it in 2 hours. Any other things that you want to discuss? Okay, otherwise then I'll see you on Friday. And for those online, I'll assign the final exam on Wednesday, which will be due on Sunday.
Okay, sounds good.
Yeah.
Am I allowed to put this in my lab 3 as my drawing?
Uh,
Or, because I thought you wanted it like finite, that you only get the 2 points.
yeah, so this is the motion shape. Yeah, I think,
Hand drawn.
yeah, so what I was thinking was more like, if you, like, original, like, shape,
Oh.
like this, and then this move by, this is M1, this is M2, right?
Okay.
So mode shape, let's say 1, 2, then it's moved by 1, 1, and then this move by 2, and then like this, right? So it's
Got it.
like, I know how it.
Someone has. Not through yet. Not through, yeah. Or, I don't mind it. It does not take that long.
Yeah,
I just overthought it.
Eigenvalues, total shapes.
Done.
Tony, do you have a question or?
Nope, I'm good. Thank you. Thank you so much.
Okay, all right. See you.
Yeah, bye. Take care.